you are losing a lot of value if you can't make it, there's an enormous return on investment for any company that's paying a developer a reasonable developer wage and sends their developers here. I can't tell you how big of a mistake it is not to send someone to CppCon.
Good morning. We are going to explore in this session a few ways of doing the same thing. I guess that you're doing that as well sometimes. You have a few thoughts about whether I should do something like that or in another way. And I had the privilege of saying, let's do it in all ways. I mean, it's not all possible ways. It's 6 ways. You can count possibly more than 6 of doing the same thing and analyzing the design choices, the pros and cons. So this is the journey that you are going to explore together. And the idea is to mainly explore polymorphism, use of smart pointers, and going towards static polymorphism. A few words about myself. I'm a lecturer at the Academic College of Tel Aviv-Yafo and teaching also in Tel Aviv University. Developer advocate at Incredibuild, member of the Israeli ISO C++ national body, and co-organizer of the Core CPP conference and meetup group. This is a t-shirt from the conference, which takes place in Tel Aviv. A slide on Incredibuild. We do build acceleration. So if you are suffering from slow builds, either on your builds, as part of your CI pipeline, talk to me. It's not just waste of time, it actually affects your dev cycles and productivity. So I'm here to talk about that if you want. So 6 ways for implementing math expressions calculator. This is linked to the slides if you want to follow now or later. I will share the slides also via Discord and all other means. So if anybody wants to take a picture of the QR. It's in Google Slides, so you can follow during the talk. So it's not this one. I have another talk called 6 ways for implementing Max. So if you're watching that now, don't decide not to see the other one. They are separate. I like doing things in more than one way, usually 6 for some reason. I mean, it's not actually 6. It's, I just say 6 and then it might be 7. So the other one, the 6 ways for implementing Max, is about implementing Max and talking about dangling references and API design, which is another talk that you can watch, but this is this one, okay? You are now here. You can see that this picture was not taken today. It was during the tech check yesterday. So the initial challenge, let's start. We want to implement something that would calculate some kind of math expression. In this example, we want to sum the exponent of 3 and 2 and -1. And then we want to print the expression and then to print the evaluation, the result. And we want the printout to look something like 3 to the power of 2 plus -1 equals 8. So the left side is the printout of the expression, and the right side is the call to eval. Okay, this is the challenge, and I'm using this challenge as a way to teach polymorphism. I started with I'm teaching C++ as part of the things that I do, and I think it is a nice start for polymorphism, understanding that we have a base class in this case, which is the base for sum and exp, and probably also number. And in order to do that, I think that we can code together. So I think that we still have time. At a certain point, I will just skip to the pre-prepared code, but now we can do it together. So if you remember, we started with something that takes sum, right? But the constructor for sum was expecting 2 arguments of which type? It was exp, like exponent, and number. But it can be generically any kind of expression. So we need to in a way, describe expression as base class. So what do you see in expression? The things that you think that are required in expression? Yeah, there was an eval. Okay, so eval should probably be something that is returning a double and is virtual, right? And I actually cannot implement that now because I'm just an expression, I'm abstract. So yeah, if we have something like that, probably in the public section, I think that we would be able to evaluate the derived types, okay? Each one with its own way of evaluation. There was also a printout, if you remember. We print. And in order to print, we need some kind of a friend function, like I'm in the extractor. And then the question is, can we do the extractor here as a virtual function? Like, usually we want something like friend. We return ostream, right? We call it operator extractor, and we get ostream, let's call it out, and a const expression, let's call it E, okay? So the question is, can we do equal 0 here? No. Can we say that this is a virtual function? No, it's a global function. So can we implement it? Yes, we can. I mean, we should, but what should we print here? Yeah, we can say something like, maybe we can print you to the standard output or to the output that was provided, which means that, okay, we need some kind of a print function. And for being correct, we also want to return out. Something like that. And then we are covered. So I think, I don't know why I'm copy pasting, because it will be maybe only for the virtual keyword. So there will be a void print and the const also, which takes ostream out, right? And I think this is, as a base class, something that can provide what we want. Okay, now we all need just to implement the other classes, okay? But because we don't have enough time, I actually created them. So here is number, okay, which derives from expression. It actually implements print and eval. So yeah, number is a simple thing. I added also a binary expression because sum and exp are quite similar. So there isn't any need to manage the deletion in the destructor by each one of them. I can do that in a base class. So binary expression is getting as a template argument the operation just in order to print the operation inside the print. So this is just a char. And when you actually want to evaluate, so you call another added virtual function which evaluates two doubles. Because I can evaluate my left end, my right end, which I do here in binary expression, and then call evaluate time PL, which will be implemented in the other two, sum and exp. And you can see that sum and exp are quite short. I mean, concise, which is good. This should compile, I hope. No, what's happened here? Okay, binary expression. I think that marked override. Oh, I forgot something. No, nobody told me here. What is going on with you? I forgot to say that you have to help me. Otherwise, I can make mistakes. But it's good that the compiler saw that because of the override on the virtual functions, on the virtual destructors. So I need here something like, yeah, I have a virtual destructor. We must have that. I don't know how we forgot it. I forgot it. Okay, it's good that we got the compilation now. Okay, so yeah, we have that. It's good. So this was the initial challenge. But something is bothering you here. What is bothering you? All the news. So there are two things. First, we have a lot of news and only one delete. And the reason is that the root is holding the entire expression, and once you delete the root, you actually delete all the sub-expressions which are managed by the root. But then the question is, can you enforce that? Is it being enforced? Well, I'm running address sanitizer, so in a way, I don't know. No, it's not the best thing to do. There is here asymmetric calls to new and delete. And the other thing is, why should you call new and delete to begin with? I mean, Shouldn't we have the rule of no new and delete in user code? I mean, don't do that. Don't use new and delete if you are in C++ 11 or above. So I think we are aiming for something that would be using smart pointers. So let's go for unique PTL. So I think that, again, we can do some live coding. Maybe we can even continue from the previous one. Okay? So this is where we stopped. And my question here is, OK, if you're going for unique PTL thing, let's just first check that we have that above. I'm not sure. No, we need to add things. So let's add memory. And let's add here. No, yeah, let's add it here. std unique PTL. For make unique, I will do stud make unique. OK, so what I want to do here as a first step is to say, you know what, instead of new, I just want to say here that I want to stud make unique, right, sum. OK, I'm creating the sum, and there will not be any need for delete. I mean, I don't like commented code. Just delete it. OK, no deletion, because the unique PTR will take care of that. This is the whole idea. OK, so same thing here, right? Maybe we'll just break the line. Same thing here. Same thing here. I could have maybe do a final place. Anyhow, we are almost done. And same thing here. OK, I think that this is what I wanted to do. This is the X, so I can break line here. OK, I think that we see here no new, no delete. But then the question is, OK, but it should, in a way, also change this class binary expression, right? For example, no need for the destructor, for sure. And the types that I hold here are not two pointers, but actually two unique PTR of expression. And the nice thing is that the star goes away. And then also the constructor is not the same, right? So we should take two unique PTRs. We're almost there. 1, 2, and then something like that. We need to stud move them, right? Otherwise, we'll just try to copy, which will not compile. OK, so we'll take the two unique PTRs. Something is OK, and the other one. And I think it seems to me that we did all we need. Because when we actually use them, they actually are being used as pointers. So there isn't any need to change anything rather than getting them and storing them. And luckily for me, it works. OK, it's good. It's nice. I mean, it's not so nice, but it's the first step. And then the question is, what is bothering you now? Yeah, I mean, let's assume that I do need the allocations, because maybe the information comes in runtime, and I need polymorphism in a way. So let's put aside the allocations. Let's assume that I need the allocations. I see here a lot of noise. I heard somebody says that. Yeah, it's quite noisy. I mean, I would like to try to hide the use of unique PTL. I mean, it would be nicer to see something like that. Why should you say all the make unique? I mean, maybe have a factory, or maybe even something easier than a factory. Maybe just, say that you want a sum, say that you want an exp. And I will create something for you which actually would use polymorphism under the hood. OK? So what makes the code above better compared to what we had before? I mean, yeah, the one underneath, yeah, we used to see something like that in our code base. No, I like better the one above. Why? Because we are hiding implementation details. The use of unique PTR is an implementation detail. The user doesn't have to know about that. We may want to change it later. It's a private implementation detail, and it is noisy. It would be much better to just hide it. So let's just try to hide it. We still have time. So I think that we can still go and think about how can we hide it here. I mean, the goal was to say, you know what? You send me a sum, OK? And you just say here exp. And you just say here, without any call for oh, I need a unique PTR, okay? Number, and here, number. That's it. But then, of course, the first thing to change would be, I mean, something changes here. What would be the first change that we need to do in above code? Change the binary expression, which has, I mean, I'm changing the call to the constructor. So let's go to the constructor. The constructor now gets different things, okay? So the question is, what the constructor is getting here in binary expression. This constructor has to be changed, right? We are not going to get any more unique PTRs. So we can think about, okay, maybe you're getting something like expression ref. But no, it was an R value in a way, so maybe expression ref. And I'm saying, no, I want to know which kind of expression you sent me. So maybe let's call it expression 1 and expression 2, just because we are going to use a template for the constructor. Because I want to catch the thing that the compiler knows when I call the constructor, which kind of actual expressions you sent me. So for that, let's have a template. It will get in sometime, type, name. We called it expression 1, which is fine, and expression 2. OK, so we have the constructor. And now that we get these two, what should we have here? So we're not moving anything. We just need to make unique. This is the time now to make unique. Make unique of what? Make unique needs to know which kind of type are you going to allocate to make unique. And the answer is expression 1. Expression 1. OK. And then I can pass in E1, which would go to its copy constructor. OK. Should I std move it? Yes, I should. Otherwise, I think it wouldn't work because it has inside, oh, I can just keep the std move. It has inside a unique PTR that should be moved. So the other one would be something quite similar. Something like, instead of the, I still need the move, this is 2, and I think that the constructor is ready. Any other change that you think is required? I mean, I got the type. I create the unique PTR. No need for a destructor. It's a unique PTR. No need to implement a copy constructor. I just, take the internal unique PTR and move it because it's in our value, the thing that I'm sending. I mean, let's just compile and check. And, oh, no match for the star operator. Oh, yeah, something here changed because eventually the type that I'm holding here was not a unique PTR. So it's an actual sum in this case. OK, so I just need to say, OK, so let's call print of E and E dot eval. They're not pointers anymore. OK, and we got it. That's good. And in a way, it's nicer, I would say. I think it is. I think. At least the user code is nicer. And it achieves quite the same thing. So yeah, that's a step. Then the question is, should we use unique PTR or shared PTR? I mean, it worked with unique PTR, but then the question is, would it work for all cases? So we have here 2 cases, or even 3. This is the first one. We actually saw that. This is another one where we std move an expression that was born before into a new expression. Is it OK? Well, it should be, because eventually it's like an R value. It's an R value which is the same as we did before. But then the question is, what about the last line here, E3? Can we pass an L value expression into a new expression? And the answer is no, we do not support that because what is the thing that is not supported? There is a unique PTR inside, so in a way we try to copy a unique PTR. Something breaks there, okay? Which is good. I mean, it shouldn't compile because otherwise, I don't know, 2 unique PTRs would be, same unique PTR will be held by 2 different expressions. It should break. But if you do want to allow that, can we allow that with unique PTRs? Or maybe we should move to shared PTR. And the answer is we can do both. I mean, we can do it with unique PTR and we can do it with shared PTR. So if we go with unique PTR, the way to do that is we actually need to clone. So if you actually got an L value, you say, okay, thank you, I will take this expression, but I cannot hold you. I cannot move what you have inside. I should clone, I should copy you, but you do not have a copy constructor. So I should implement a clone function. And since deducing this would come only in C++23, we will use CRTP. So we can add the ability in binary expression, knowing the actual expression that it manages, we can manage something like a clone function somewhere. Here is the clone. So the way to clone is to rely on the actual expression that was passed to us based on CRTP. And say, okay, we can create a copy with make unique, and here inside you call the copy constructor, which we need still to implement. But to implement that is not so complicated, we just clone both sides. So eventually, yeah, you can clone something that holds a unique PTR. You just need to implement that. And once you implement that, you actually support also the L value case. How can we support the L value case? By supporting, let's see, when I get the expression here, and I call make unique here, then in the case of L value, when it gets in, it is being copied. When it gets in, there isn't any copy elision. It gets in, it is being copied here, inside, getting into the function. And then, since now I have a temporary, I can move from it. So yeah, we do support now also this option. Then the question is, okay, can we do that with shared PTR? So once we saw that we can do it with unique PTR, the question is there any advantage of preferring, of thinking about shared PTR? And the answer is, first, yes, we can do it with shared PTR quite easily. No need to implement clone. And second, yes, in some cases, there will be advantage of using shared PTR. And the reason is that if the object itself is costly, takes much memory, okay? And I don't want to waste the memory because eventually it's an immutable object. If you follow, I don't have any setters. You just create the expression, and in my case, it is immutable. So once I hold a copy, I didn't have to hold the copy, in fact. I could hold the same thing. But in order to hold the same thing, one needs to know when to deallocate. And for that, we have shared PTR. So if we think about, I think the design pattern is flyweight. If we think about, you hold the same thing. Why should you use a copy? So don't. Now, in this case, the copy is quite cheap. So think about unique PTR, shared PTR. I don't know. Both can work. But if the copy is, copy in memory, if the memory required for the object is quite big, I would think about going with shared PTR. So the implementation with shared PTR is quite easy. I just change here shared PTR from unique PTR to shared. That's it. I can change here to make shared. I can keep make unique. It would work as well because there is a conversion from unique to shared, even though if you are creating shared, just say make shared. And that's it. No need for clone. And I do support the thing here. And then the question is, if I have an expression, I hold E here, and then I change E. E gets being override with a new expression. Would it change E2? So E2 is holding E, okay? Based on shared PTR. And then I'm changing E. Would it change E2, which is holding E, let me rephrase, which got E as an argument when born. I got an E when constructing E2. Then I override E. Then I print E2. Would I see the new part of the new E, or the E that I hold will be the old one? What do you say? So the answer is, it would be the old one. It will not override. Why? Because once you do the assignment, then you actually change your own internal shared PTR to a new one, and we actually get here the behavior of copy on write. So we have, for free, a copy on write, which might be that this is the thing that you wanted, which resembles something that we call today value semantics. So we got a value semantics with polymorphism in a way that you don't really need to expose to the user the fact that there is polymorphism. I mean, the user sees all different kind of classes here, but I do not bother the user of being aware of the class hierarchy, being aware that there is dynamic allocation, using, on the user side, unique PTR or shared PTR. It's an internal design decision, which I think is good. And then there is some kind of noise that I want to get rid of. What is the noise that still bothers me a bit? Something that we can rid of. The number. I mean, 3 is a number, isn't it? Why should you say number? I should say number because 3 is a number, but it is not an expression. And the constructor is expecting an expression. How can I accommodate a number, a literal, and not a number, like the class number? Something which is, okay, it's not an expression, but I can turn it into an expression, I mean into a number expression. How can we do that? By overloading, adding another constructor. So if we have another constructor, we can actually say, you know what? We can take expression or we can take numbers, okay? So let's do that, okay? What we want to achieve is you don't need actually to say number. You can just, send me literals if you want, or actually integer variables or any variable that you want, which can be converted into the number expression. So yeah, it would be nicer. So our first attempt would be here, and then I would ask you what is wrong, and then we'll ask how can we fix it, okay? So this is our first attempt. And in our first attempt, by the way, which class should be amended? Which class should be touched? Binary expression. Number is number. When you want to create number, and we will create number internally, we just keep it as is. But in binary expression, we want now a few more constructors. So let's take a look. So the first one says, okay, I'm taking 2 expressions. The second one says, I'm taking an expression and a double. Then we have a double and expression. Then we have 2 doubles, which actually covers all cases, I guess, for 2. Okay. Now, there are a few problems here. First, I feel that there is some repetition. Maybe we can do that with less repetition. Okay, we'll think about that. And the other problem that bothers me, of course, when we get the double, we actually create the number inside. It's an internal decision, right? No need to bother the user for that. But then the thing that bothers me, take a look at the main. Something changed here. I mean, I don't say number anymore, but it is not exactly the same thing that we saw in the slide. I had to do something here to make it compile. It is doubles. I mean, can we send integers inside? Well, integers can convert themselves to double. Should it work? Yeah, there is a better match by the template, which is quite greedy. I mean, if this one is a int is not a double, and there is a better match. And the better match is the template thing that says, oh, come to me, sir, I will treat you well, you are not a double, and I get anything, I'm quite greedy. So the template that gets 2 expressions, which are template arguments, would be preferred, which is not the thing that we want. And then we try to create an expression of that. An expression doesn't have, I mean, this is double, int, sorry. And the thing here, we can make unique an int from an int. That would work. It cannot get into E1, because E1 eventually is a unique PTR or a shared PTR to an expression, not to an int. So it doesn't fit. I need something which would be an expression, okay? How can we deal with that? What should we do? I mean, I do want that. to be allowed, to be supported. A question?
So can you basically just have an adapter that takes an expression template and it gets specialized? So if it actually gets, if it's a number, if it's a double, if it's a float, it's going to wrap it into a number.
Yeah, here, a good idea here. That's a good idea. So the idea here is saying, you know what, maybe you should take both, all cases in one constructor. Is that the idea?
Yeah.
And then inside, send them to some kind of a factory saying, okay, given this argument, I want to turn you into an expression. Now, if you were an expression, then you'll get a make unique of the expression. Otherwise, you'll get a make unique of a number. Yes, I will reach that, okay? But before that, I want to do it step by step, okay? So the first step would be, let's keep the 4 constructors as is, which I don't like, the 4 constructors. I would like to go with something like an adapter, but maybe we can amend the constructors, or specifically the first one, and the others in a way for the template argument, to be less greedy. How can we make them less greedy? Yeah, we can require them to be less greedy. We can use C+20 concepts and say, you know what? I can take an expression only if this one is an actual expression. Don't take anything. So the way to do that would be to say something like requires what? What should we require? STD, it's not same because it's a hierarchy. So it would be derived from, I think there is. We should add concepts in the includes. And what I want here is expression 1 to be derived from expression, right? And I think that we also require, I think that for that we'll need a parens. We also require the same thing for the second one. Something like that, okay? So if we require them to be less greedy, it will not get here. Now, we need to do the same thing. Let's just check that it compiles. I mean, maybe it... No, so the problem is it didn't go to this constructor, okay, because we still have others. But we need to do the same thing, I think. Yeah, we need to do the same thing for the others, right? Same thing here, but here only for expression 1. So once we say, okay, don't get in if it doesn't match, then we will send you to the right one with int, which is what we want to do. So I think it might be that by narrowing them, oh, we don't have the include, but somehow it gets in from somewhere else. Okay, so yeah, we narrowed the thing. Okay.
You can make the code better to, like, by replacing the type name.
Oh yeah, sure, of course, we should do that. I'm with you. So the thing that we should do is, instead of all the requires here, we just say instead of a type name, we just can say derived from expression. Totally, I'm with you. So if we say that and then, sorry, that, and then concepts work like when it is on a type, then the type is injected as the first argument into the concept. So we need the thing to be derived from expression, which looks nice. And the thing here, same, to be the same. I would say that this would be much nicer. Yes, thank you. And then we can do something quite similar in the other cases. So here it would be without that one, right? And here it would be with the only change is that we call it expression 2. Nicer, right? The more concise version of using concepts on template arguments. And it works. We can even do that maybe on the type here, if we want. We can say, how to derive from expression, how to, this is the third option of doing the same thing, right?
Is it still unfortunate that you're converting to double? In your mind?
Should I convert to double? I mean, I converted to double from int. Yeah, it's fine. I mean, eventually I old number as a double, so it goes in as a double. It's fine. It should be converted at some point. This is the next step. So we saw what is wrong. The template was too greedy. We actually went to this one. Okay, let me see what was my original implementation. I think that I used here, yeah, the shorter version originally. And again, it can go here if you actually want, with derived from expression auto C+20 auto arguments.
But then you would have the decal type on 39.
Oh, it might be that something here would be missing, like I will catch it with reference. Yeah. So anyhow, yeah, and I need it here. So eventually, I think that I do want the template. I need it. Yeah. And I still don't like it so much. And the reason is that we have the 4 versions of the constructor. Now, 4 is not so much, but if you have a variadic template, or 3 arguments, or 4, so the number of combinations is too big. I mean, we should think of something like an adapter. One constructor that takes it all and then sends the arguments to a factory or to adapter saying, okay, I need you as an expression. So this should be our next step. Let's take a look. So with our next step, we actually have, this is our next step? No, something is wrong here. It might be that I put here the same link. Oh, that's a mistake. Okay, it's the same link. So let's do it together. I mean, it should have been a new link, which is not. We still have time to write it. Okay, so the idea is that we don't want all 4 constructors, right? So we actually want one, and the one that we want is this one in a way. I'm just, removing the others, but since eventually I do want a function for a wrapper that would be called toExpression, so I will use some of the code from underneath, so I'm not deleting it yet. Okay, so toExpression will return something like, I would say, unique PTR of expression. This would be the adapter. Okay, and toExpression will take template argument that would be anything like type name. Maybe we should have 2, like 1 for double and 1 for, yeah, that can be the case. So we can have 1 for, are you an expression? Oh, in which case we can do something specific. And in other case, we can do something else. So if you're derived from expression, we'll call you expression 1. Then expression 1e will do one thing. And then we can have another overload for otherwise, in all other cases. I mean, I can say that maybe you are a number. I can require you to be a number. But I can say, you know what, otherwise you will not compile. So I, in a way, assume that this is a number. I can call it num, or I can just call it t. And this toExpression, which gets a t, would assume that this is a number. Okay, so what should we return here? Something like this one, right? This is the thing. Okay, we call it E1. This is the thing. And what about the other one? We have it. The other one is this one, right? So the other one would say, okay, return E1 to E. Thank you. We have your human compilers. That's good. And here, return, make unique. Oh, the template argument. No, I called it expression 1. So that stays, I think. So this one should make unique a number, should make unique, I think. How come? Maybe in this version I add using for that. Anyhow, let's call it t here. Or we can call it num, I don't know. It's a num. It should be a num. Okay, so we have the 2 versions. Now, once we have the 2 versions, I can omit the constructors. I should change the link in the slides. And all these can go away. And I can go with one constructor that takes 2 type names. I can still call them expression 1, expression 2. And then send to E1, E2. What should I send? It should be toExpression. And I can still move it because, move it all the way. And then toExpression here as well. Yeah, I think that this should suffice.
There's some extra braces there, maybe.
Extra parents.
Go on,
2 on that side and 1
line 42.
line 42. Line 42. Yeah, it seems so. Okay, thank you.
Braces, color braces.
Oh,
Near semicolon.
And semicolon.
thank you. And what about that one? That one is okay. Here it seems that also too many or 3 on that side? No. Okay, let's make the compiler do the parsing. So yeah, we have too many. What's the problem here? Make unique of number. Let's read the compilation error. I mean, I'm telling my students usually first read the compilation error, and I don't do that. I rushed, which usually maybe you do the same. Rush to amend the code without. No, let's read it. Expected semicolon on make unique. Oh, extra parens here. So we did have an extra parens. And yeah, we have it. Okay, so eventually we have one constructor that deals with all cases using the very simple now one argument adapter, which is much better than handling all combinations. Why should you handle all combinations? And this is the third case that I should share into the slides. Let's do it now. I don't have time later. I may forget it. So this is the actual link that I wanted. Same here. And this is in a way a design target that we reached. So I think that we have here, we didn't finish, but we have a design pros for this code, which is a simple usage, short and concise, hiding implementation details, and we're using polymorphism with value semantics. Nothing can be like shared without being handled correctly. But still we can do better. Do we need to derive classes from sum and exp? So we can think about why should we derive from binary expression. Maybe we should pass to binary expression the operation to be performed. And the reason to get away from the inheritance is that you all know that inheritance is the base class of evil. I mean, if we can delay the inheritance, if you can say, you know what, you're a binary expression and this is what you do, I don't need to derive you from binary expression, we get some kind of reduced coupling. We decouple the types. And this is also a step towards eliminating the need for polymorphism to begin with. I mean, so maybe you can go with templates all the way. So in order to see how we can do that without the inheritance, we would say that binary expression is getting an operation. And then it is using the operation, here with the long thing that, yeah, we can use the adapter. And using the operation, I actually call eval on the operation without requiring any kind of inheritance. You just provide me the thing that you want to perform. That's it. I mean, why should I require you to inherit from something if you are coming with required functionality, duck typing? I mean, there are libraries that work like that. I think of STL, for example. So eventually, the operation itself is quite simple. I mean, it is simpler than what we had before. I just express the mathematical operation and my character, and that's it, in a way. Now, I do want to, in the user code, not to say binary expression of sum op, binary expression of expop, so I'm giving them a name. I can give them a name in a more safe way if it is required. Here, it's just a type def using, but anyhow, eventually, I get the same without the need to inherit sum and exp, which I think, I mean, it's a question. Maybe you do like the inheritance, but it does have some limitations when you are required to inherit. So I think that we have here a design pro that narrowing the inheritance to the minimum required is something good. And then the question is, can we implement it without polymorphism to begin? And the answer is yes, static polymorphism, templates all the way. So what we can think about is maybe binary expression by itself can be expressed based on template arguments. So binary expression holds expression 1 and expression 2. Yeah, we can do that, right? So in order to, why is it better? So it is not necessarily better. I mean, it might be not sufficient for a use case. In which cases? If we create the expression in runtime, if the expression that we hold should be created, parsed and created in runtime, and then, okay, you still need to preserve some kind of polymorphism, runtime polymorphism. But in case the expression is being created at compile time, by the way, the actual arguments for the expression can be provided in runtime even if you're using templates, because they are provided for the constructor. I mean, the numbers that go into sum, exp, etc. Okay? The expression tree itself, the structure of the tree, should be known at compile time if you're going with a template approach. So it is a bit more narrowing. I mean, it's only for compile time for the structure of the tree. But if you know the structure of the tree, the structure of your expression, then it is good. You can check it at compile time, for example. You can constexpr it. So let's see how we can do that. Binary expression, actually we don't need expression anymore, because you just create binary expression, that's it. And binary expression is templated over expression 1 and expression 2. It gets both. I actually don't know what I hold here. As long as it can be eval, as long as I can send it to the op that I get. And then we have some op, which knows how to print, and which knows how to eval. And then we have expop. And then, just because we want in user code to use sum and exp and not binary expression, triangle, brackets, whatever, I just want to create. So I could use using sum as, but I need here something like a specialization for I know what is the sum op. And you cannot specialize types. So I think that the only option here is to have an inline function, constexpr, that would create the binary expression of sum based on 2 unknown template arguments and 1 known template argument. So I actually create the binary expression. The user would not see all the boilerplate. The user will just use sum or exp. And here it works. It is a bit shorter.
Can he use templated using?
Yeah, I can. But not if I want to provide one argument and to deduce the others. So if I think, as far as I remember, that if I want to create a type or to declare a type like using a name of a type based on I can provide the template arguments, it is either deducing them all or providing them all. And as far as I remember, you cannot deduce part and provide others for a template type. Anyhow, it is being solved with, okay, I'll just create the type and return it to you, and it doesn't cost anything because it's a constexpr inline function. And that's not the end of that, because what else can we add? I mean, what would be our next challenge? You all know. We used concept somewhere. I mean, we can narrow that to something, maybe. I thought about variadic templates. I mean, why should we just add 2? Maybe we can sum any number. It's true that exponent can exp only 2. I mean, some of the expressions are binary, but some of the expressions are not. For example, sum. So let's make sum variadic. Now, the challenge here is, if you remember before, binary expression held 2 expressions, expression 1 and expression 2. And now that sum is going to hold any amount of arguments, any amount of sub-expressions, we have 2 options for that only. Using inside a tuple or a tuple, as you prefer, right? So we are going to use inside a tuple, or if you call it a tuple, and this is what we are going to have. So we have an expression. An expression is based on operation and any amount of operands. And then we hold it inside a tuple, because eventually we'll use it only later. We are lazy. If we can immediately in the constructor do something, then maybe we do not need to store it. But since we are going to evaluate it and print it later on, we must store it somehow, so we hold it in a tuple. And then the constructor just, move all things, because we got it by value, move all things into the inner expression. And we actually can use, based on C++17 to apply, we can unpack the tuple into their print function, which is what we do here. And using to apply, we can unpack the tuple into the eval function of the operation that was provided. And the operation might be binary. It's fine if it is a binary operation, or it might be any kind of operation like sum is variadic. We add here casting to a double, and the reason is that we want to accommodate integers and doubles and numbers as is. We don't want to call when we plus things. We just want to take the argument without calling a val on that. Then we call then sum op is quite easy. I mean, the print is first print the first. Then using if const expression, if the size of the tail is more than 0, then just continue by calling print again, right? Easy. And evaluating is either return the one that you have or return the one that you have plus all the others. That's the nice thing with variadic templates, they are easy. Eval of E1. So I think that you're right, but maybe because I have this one, then yeah, it works. But I'm with you. Maybe it would be better to say eval here on E1. Yeah, makes sense. Once we have that, exp is only for 2. I mean, if you will try to call exp for more than 2, it will shout on you that it cannot call print, it cannot call eval, because eval and print are supported only for 2. And then I have the sum elpo function, like the factory creating sum as an expression of sum op and all the variadic pack. And I have the same thing for exp. And in the main, I can actually create the variadic pack of sum. I'll take questions at the end. Let's take 2 questions, and then I have some time to summarize.
Oh,
yeah.
no, just a nerdy comment. I think on the sum op, you don't really take expressions, you take values in there. Am I not wrong?
No, I'm actually taking expressions because here inside sum, there is an exp getting in. And when I print it, I actually want to print it as this thing, as not and not as 9. So I actually want to preserve the actual inner type. This is the reason. Thank you.
Just a remark, you're taking a variadic template and you didn't take care of the situation where there is no argument?
So the question was, sorry for not repeating the previous one. The previous one was, are you actually taking numbers or expressions? And the answer is, I actually need to treat expressions. And this question was, are you dealing in the variadic case with 0 arguments? So sum, I'm not allowing sum of 0 arguments, but I am allowing sum of a single argument, which sounds fine for me. I do not allow summing nothing. Okay, so this brings us to the third. I think we had some stops on. Okay, this is a nice design that you want to take points from, and I think this is one of those. Static polymorphism. To summarize, C++ is a multi-paradigm programming language, and I think that we see it here. We can do things in more than one way, and here I think that we saw 2 or 3 ways. Like hiding your smart pointers, you should do that. But then, should I use unique PTR or shell PTR? Well, it depends. Do you have a small object or a large one that you do not want to clone? We saw static polymorphism. We saw dynamic polymorphism. We talked about, should I inherit the operations, or maybe should I go with duck typing and provide the operation as a template argument? And I say there is a point in saying, maybe I should avoid the inheritance. Maybe I should delay it, or use it only if actually required. Go with duck typing. You would allow more template metaprogramming and accommodating types which are not part of your hierarchy as long as they provide the required functionality. Pointers, references are not mandatory for polymorphism. The entire code was using value types. And I would say quite efficiently, because those value types were actually holding internally smart pointers. So I don't pay for anything, I just hide the fact that there is polymorphism and that I need pointers. Prefer using smart pointers for internal members and do not expose them because you may want to change things later. It's a private implementation detail. Try to hide your smart pointers exposing value type semantics. And I think this is an example of how to do value type semantics. When using unique PTR, you can still copy. In some cases, we think that a resource that we manage cannot be copied because it holds a unique PTR inside. Well, you can still implement your clone function and come up with, oh, I can clone and create another copy of that unique PTR, a new one. That's fine. You can do that. Using shared PTR to hold immutable data is an easy way to achieve copy and write. We had copy and write, and in a way, it's kind of a flyweight design pattern. I share. And I do not share in order to mutate, because maybe you heard that sharing is not caring when you mutate from several threads. I share the immutable state. Static polymorphism may replace dynamic polymorphism. Consider this option. It's not always the case that you want that. And if you do that, maybe add static asserts, concepts to like narrow your greedy templates. Don't avoid using templates because of longer compilation time. There is a solution for that, and maybe you remember there's a company, Incredibuild, that do build acceleration. And a credit note, thank you for Arthur Dwyer sharing valuable comments on the previous version of this presentation. Thank you to CPP Bay Area and Haifa C++ meetup groups, again, for fruitful discussion on a previous version of this talk. Any questions before we conclude?
Hey, thanks. So, not really a question. I just wanted to add a couple of things because this is really close to what some of the C++ compilers are doing. And basically, they are using a couple of tricks to make this really efficient, the dynamic polymorphism variant. For example, they pool the allocations for better memory locality. And the other problem, when we, for example, use unique pointers, if we have a really big AST, basically we can run out of stack space when the distractors are running. So some compilers end up ensuring that all the nodes in the tree are trivially distractible. So basically they can just deallocate all the pool without running any of the distractors. And sometimes, since the compiler after it is done with processing the AST, the process will be killed anyways. They wouldn't even bother deallocating the pool because they would do it at shutdown anyways.
So thank you for the comment, and I hear that as it is actually useful what you present here. Thank you.
Yeah, and I also think there's a proposal for value types in SDL, stood : polymorphic and stood : indirect, which are basically do a lot of that, and people can look it up.
Yeah, so things similar to that can come up as part of the language, but even if it is not there yet, you can and you should implement that on your own when you need that. Thank you. Thank you, everybody. I'm here for additional discussion if anybody wants. Thanks.